Hello, everyone. We are the group Taco Bell Crunchwrap Supreme, made up of myself, David Pokras,
I'm Jake Fulton.
I'm Aaron K.
and we had one other group member who helped us work on this, who worked on the ME154 part exclusively, and our project is the vegetable slicer.
The kitchen is a dangerous place, especially for the elderly and those who suffer from impaired mobility. Because not everyone could be Gordon Ramsay and chop as fast as him, we needed to find a way to make it fast, easy, and safe. Our solution was to create an easy-to-use, hands-off system that significantly lowers the chances of bodily harm occurring while still maintaining portability and cut consistency. Hardware and software are used to place obstacles between the user and the dangerous parts, allowing for safe chopping and the ability to multitask. Compared to our original design, we changed it by a couple centimeters in width, length, and height. Our power source was changed from 120 volts AC to 12 volts DC and 5 volts DC from the jock. The prototype ended up costing way more than we expected, totaling to about 3 times the cost at $100. We never considered chop efficiency originally, but we can now guarantee 100% chop efficiency. As for the chopping speed, we decreased that while increasing the pushing speed.
We used a lot of different components in this project. We have a stepper motor to push the vegetable down the track, a DC motor to move the blade back and forth to cut the vegetable, a button to start and stop the system, photo interrupters to tell the code when the enclosure is on or off and where the knife is, lever switches to limit the motion of the pushing mechanism, a potentiometer to control the speed of the pushing mechanism, as well as a current sensor and LEDs that can help us understand what's going on in the system at any given time. Here's the block diagram for our system. We have 5 digital sensors made up of 2 limit switches, 2 photo interrupters, and a button, as well as 2 analog sensors with the potentiometer and current draw sensor. We have 2 system status LEDs, one that's green when everything's normal, and one that's red whenever the current draw sensor reads a value above a given threshold. The ULN2803 transistor takes a PWM input from the microcontroller and 12 volts from one D-Rock power supply and outputs a PWM signal to the 12 volt DC motor. The LN98 driver board takes a digital input from the microcontroller and 5 volts from a second D-Rock and outputs a digital signal to the stepper motor.
Designing the circuit was one of the most time-consuming aspects of the project due to the numerous subsystems. However, once the schematic was complete, the physical wiring was not nearly as challenging as it would have been otherwise. The microcontroller is represented by the white box in the top right corner labeled Feather NRF52840, with the L298 motor driver board to the right of it. Pins D6 through D13 are used to send digital signals to the L298, which then passes 4 digital outputs to the stepper motor, shown below the L298. The DC motor in the bottom right corner of the page is controlled by the ULN2803 Darlington transistor array. The positive terminal passes through the current sensor, which is in turn connected to the I2C pins on the microcontroller. This is to measure the current the DC motor pulls to light the red LED. The base of the ULN2803 is connected to pin A5 on the microcontroller. The entire left half of the schematic shows the various sensors that are in the system, as well as their respective current limiting resistors. This was an important point of our consideration, so we studied the data sheets and picked resistors with the proper values to ensure that the GPIO pins would not be damaged due to current overload. To the left of the transistor array are the 2 LEDs connected to pins RX and TX, which are both set to digital outputs.
The code is a state machine, which has 5 different states and 5 events in addition to event none. Basically, we're moving forward through vegetable pushing through the knife, and once it reaches the knife, we pull back, and the different events are what move it between the different states. This can be more clearly seen in the state diagram, moving from state ready, pressing the button to move to state push, and then it moves between push and push wait as the knife is extended and retracted. And then once it reaches the end, the lever switch 1 moves into state pull, and then it pulls back until lever switch 2 is hit, which then it moves into state ready. The main things to focus on are that pretty much after you press the start button the first time, anytime you press it again, it's going to move into pull wait, and it moves into pull wait as well if you can take the enclosure off, which then you have to press the button to pull it back, which then you'll need to press lever switch 2 to get it back into state ready.
And go.
test right after with the potentiometer. Or the, yeah. Next, we will transition to what we all did and learned. My portion of the project was mainly centered around the stepper motor and all the components that went along with it. This includes the design of the casing and all of its related sensors. The entire list is presented on the slide. This was a challenging task for me because throughout the class, stepper motors were one of the topics that I was most confused on. But after a lot of research and going through labs and lectures, I was able to get it done. Additionally, I was able to integrate it into a state machine system that relied on the use of 3 different sensors creating events to move between states and a potentiometer to change speed. Adding on to this, I also learned new skills in practice wiring. Soldering was new to me, but very good to start learning, as I will definitely use it more down the road. I was also able to solidify my understanding of building circuits compatible with the microcontroller. Lastly, one big takeaway that I have is designing for fabrication. Final piece came out a lot differently than what was modeled on the computer and required a lot of problem solving during construction that I did not plan for. In the future, I will look to take into account the actual building of the product, so I won't have to worry about things such as mounting, loose wires, and tolerances.
I was designated with writing the code for some of the sensors that our project used, mainly the photo interrupter, the start button, the current sensor, and the LED sensor. For the 4-bar mechanism, we designed and analyzed that as part of a group, working together to ensure that our mechanism would work if everything went perfectly. I collaborated with Nico from our ME104 group to design and modify our project in SolidWorks. I really learned a lot throughout the duration of this project. In my part of the project, I learned a lot about sensor coding and making the sensors perform the way we wanted it to. My background for coding is a little shaky, so this project allowed for a lot of revising of the basics of coding as well as learning new concepts. I also got the basics of soldering down from David, as I had never been exposed to soldering before this, using the soldering to connect the pins to the wires on our sensors. I also learned how to work with SolidWorks files and use them in conjunction with a 3D printer, where we 3D printed a majority of the components for our physical prototype. I also realized that 3D printing requires a lot of time and generally has a decent chance for error, so in the future we should allow for more time to print if we were to make this in the future.
For this project, I was designated the role of integrating the 12-volt DC motor into the system. This included writing the code to output the PWM signal and setting up the ULN2803 transistor array in conjunction with the motor to work with the microcontroller. Since the wiring got a little chaotic and stuff started coming unplugged, I also removed some of the unnecessary jumper cables and replaced them with 18-gauge solid core wire that I measured out and cut to shape. While the whole team worked on designing the 3D printed parts, I did use my own 3D printer to fabricate them. This took a lot of time as revisions had to be made and parts needed to be reprinted, so I would definitely allocate more time for this step in future projects. I also had experience with soldering, so I was able to do a lot of that while also helping my team members learn. This was my first time using a Dremel rotary tool. I used it to cut the acrylic sheets that would be used for the enclosure and then change tips to sand down the pieces afterwards. I also learned a bit about the logistics side of taking on an open-ended group project of this scale. I really understand now why project managers are so desired in the professional world.